Next we go to problem 563, and in this problem we have a smooth uniform road AB, right? And it is supported at point A with the ball and socket, and then at B it is lean smoothly against the wall. The wall is actually on this YZ plane, right? And at B also it has is attached to a cable, this BC cable, which is again it is on the YZ plane, right? With this 0.5 meter and 1 meter, and we are given the dimension here. A to B is 1 meter, 1.5 meter, and 2 meter. Okay, so this is a smooth uniform road, and then it has a mass of 20 kilogram. So the question asks to determine the components of reactions at A. Okay, that's the reason why question asks components, which means that you need, because this board and socket, you need to have AX, AY, and AZ. And tension cable, which is BC, and also the wall. Normal reaction at B, which is from the wall, right? And then when we say that it's a smooth bar, so there is no friction, right? So let's draw the free body diagram. So to draw the free body diagram, we remove the supports. If we remove this board and socket at A, board and socket, we have AX, Y, and AZ. So okay, just assume the positive directions, AX, AY, and Z. Okay, and then at B, you have is a smooth bar. So basically, you have just a normal force. Let's name it as Pro B and B. Okay, along the X direction. Okay, because it's normal. There's no friction because it's smooth. And then at B also you have the cable, because we are drawing a free body diagram for the bar, so we remove this cable. And remember, for cable we have the support in the form of line of action, right? So let's name it as TBC. Okay, in the YZ plane, right? And the direction is like 1.5 and 1 meter. Okay, we'll talk about that later. Is it all? No. Actually, we have another one. We have the mass of the bar. So the mass of the bar is 20 kilogram, which means that the weight is 20 times 9.81 Newton, right? The location, what's actually the location of this equivalent load of weight? It will act in the center because it is a uniform bar, so it will be in the at the center, which means that I'll draw it from here. Okay, you go this half, okay, and then this going going this way, half of that, okay, half of that going this way, and half of this. Okay, so where's the location of this weight? It is, because it's uniform, so it will be in the middle. So it will be half of this, right? Half of this, and half of this one, which is this, half of that, and then half of this height, because the total height is 2 meters, so it will be half of that. Half of that, okay? 1 meter, right? So this is the full free body diagrams. Full free body diagram. And so we know the unknown reactions are AX, AY, AZ, and B, and TBC. We have 5 unknowns. Okay. Okay, do you realize here actually this one will be a slightly different with what we have done before, okay, in the previous examples. The reason is because in this one is fine, AX, this one is fine, AY, AZ. I mean they follow exactly, it's just it has a component of X, Y, and Z, right? And this one is fine, this is Z, isn't it? The direction is Z, this way. This NB direction is positive X, so it's fine. But this TBC, actually it has 2 components. One is in Y, and the other one is in Z, right? So if you want to solve without using a vector to solve, so actually you need to resolve TBC into Y and Z, right? And then you can do like we have done before. But here, what I'm trying to do is, I will keep this TBC, which has 2 components, Y and Z, and we'll try to solve by using the force vector. Okay, you remember the force vector in the 3D part of this rigid body equilibrium? So in order to use this force vector to solve, so we need this. First we need, okay, let's name this as G. G is center of gravity, okay, this point. So we need this RAG, okay, the position vector RAG. So what's RAG? From A to G. How do you go from A to G? First X, Y, and Z, okay? Follow that one. X, we go minus 0.75i. I, it means X, acceleration, okay? The component of acceleration. 0.75 is half of 0.5, right? Minus 1 point, minus because we go negative direction. And then for Y we have plus 0.5j, right? Half of this m, this 1 meter. And we go up plus 1 k, right? Half of the 2 meter, right? That's one thing. Another thing is we need this R A B. You will see that why we need to have these position vectors. RAB is simply minus 1.5, okay, should be double of this, minus 1.5 meter, okay, that's right meter, okay, minus 1.5 meter plus 1 meter, J, 1.5 plus 1 plus 2k, right? And then the unit is meter, right? And because we want to solve in vector form, so we need to make them as vectors, like this, W. Remember in quiz 1 that most of you actually didn't consider this? The weight here, though we know the direction is going downwards like this or whatever, so the weight is 20 times 9.81, that's fine. So if you hit the calculator, you get 169.2, okay? 169.2 Newton, that's fine. But here, because it's a vector, so you need to put the direction, which is k, z, and then minus, right? Because it goes minus the direction from z, right? And then the direction is in k. Is it okay? And then the unit is Newton. It's okay. Because when we want to do the vector multiplication method, the cross product, we need this I, J, and K. Otherwise, we cannot do that. That's actually the thing that most of you probably, unfortunately, got stuck while doing quiz 1. Okay, same goes with AX, AY, and AZ. I mean, AX will be AXI, AYJ, AZK, right? NB will be NBI. TBC will have, okay, we'll talk about TBC as well. So TBC is in a vector form. So you resolve into the X, Y, and Z components. So for x, y, and z components of this TBC, you know that this distance is 0.5 meter. This distance is 1 meter. So what about this distance? Let me write it another way. TBC here. Okay, is it fine? So what about this distance? This distance will be the hypotenuse, which is 0.5 squared. 0.5 squared plus m1 squared. 1 root, which is 1.5 squared plus 1 squared, 2 squared, root of that. It is 1. So this is 0.5, this is 1. So this one will be 0.5 squared plus 1 squared. 1 squared will be, root of that will be 1.25. Root of 1.25 meter, which is like 1.1 something. Okay. Okay. So TBC. To find TBC, then we have to resolve TBC into x, y, and z. Does TBC have x component? The answer is no. Why? The reason is because you can see that actually it lies on y and z plane. Okay, so there is no I component, no x component. But how about y component? Yes, so you have minus TBC. Okay, for the y component is j. But how about this? How do we find this component of y component of TBC? So we use this relation. The y is this over that. Okay, so it will be 1 over root 1.25. What is this? This is simply actually cosine of this angle. Okay, so this is trigonometry. I'll just give brief thing so that if you think you don't understand this, please go back to trigonometry, right? Okay, and then the z component, you see it goes this way, y, and then it goes up, positive. So it is positive, okay, TBC, and that is a component of that, and it's k. So how do we do that? Then use this 0.5 and root 1.25. So it will be 0.5 over root 1.25, right? So, and of course NB will be NBI, okay? AX will be AXI, AY will be AYJ, and AZ will be AZK, right? So we have this. Why do we bother to have this? Because actually we need to use the vector form. To use the vector form, then here actually to find the unknowns while using vector form, the best way is actually again when you use moment, we have to try to eliminate the maximum number of unknowns as much as possible in one single equation. So you can do mx equal to 0 or my equal to 0 or mz equal to 0 or whatever, even mb equal to 0. But what is the point? That's the thing. So I think the most important, the most easiest one here is probably you can try to do moment about point A. Because you see, if you do moment about point A, AX, AY, and AZ won't have moment because they act, all of them, they act at point A, so that they don't have arm, right? They don't have, in vector form, it means that they don't have this arm, right? So you will have only the components of this, the moment due to this, and that, the weight, NB, and TBC, right? So let's do moment about point A equals to 0, right? It's in equilibrium. So we don't have AX, AY, and Z in this MA. We do have this due to the weight. So remember, this is the vector form. So to have the moment due to the weight of 20 kilogram, so we need to do you have learned about this before. R A G, right? The vector R A G cross W, right? R A G cross W. Remember that to find the moment of forces in vector form, and then plus R A B, right? Cross product, cross R A B cross N B plus R A B cross E B C. All these are vector. R A B cross N B, R A B cross T B C, right? As you can see, actually here these two, you can simplify them to be, because they this plus this, so basically it will be N B plus A B C. Okay, you can factorize, right? It will be the same. To simplify, okay, equals to 0, right? So now your expression will be in this form. So remember, although this looks like one equation, actually it has a couple of equations, probably 3 or 2. Okay, so don't worry. Actually, we can solve. I'll show you. We can solve this NB and TBC right away from this equation, right? So how to do this cross product? So RAG cross W. So RAG is, okay, when we do cross I, J and K, X, Y and Z component. Again, this is math, okay? Go back to that. RAG is, the X component is minus 0.75. The J component is, what? 0.5. The K component is 1, isn't it? And then W, the X component is 0, the Y component is 0, the Z component is minus 196.2. Right? This is this RAG cross W, right? And then plus RAB cross this. So again, I, J and K. RAB is minus 1.5 I plus 1J plus 2K. Cross NB plus TBC. NB is NBX, isn't it? Sorry, NBI. So NB plus positive NBI, right? Plus TBC. So TBC has J and K. So that's why they don't overlap. You can, this is for the X will be NB, the Y and J will be for TBC. So the TBC will have this component minus TBC over root 1.25, right? And then for the K, for the Z component, you have 0.5 TBC over root 1.25. Okay, so we go back up, eliminate this. This equation, okay, so just remove this for now. Okay, so we go back up again. Based on this, we go back up. Okay. So what happened here? You can write the full I, J, and K, right? Sorry, equals to 0. Equals to 0. You can use you can write the whole I, J, and K components. So for this one, the X component, the I, will be, you see, take this. Again, this is the basic math. You should be able to go back and to understand this. If you don't, please go back and see how to do that. Okay. So for the I component will be 0.5 times minus 1.62.2, 1.96.2. Okay, this times this minus this 0 I, right? the j will be so the j will be minus this time that minus 0.75 times minus 1696.2, right? And then minus 0. Okay, and then will be j, right? And then the k will be 0, right? The k times this will be 0. That's fine. So this is from the RAG cross W, and then you do this, another vector, cross product of vector. So for the I, it's quite long actually. The I, you will do this, right? So the I will be 0.5 TBC over root 1.25, right? This one times 1, but minus this times this, so it will be plus 2 TBC over root 1.25. This is the I, right? The j will be was it 1.5 here or 1.5, right? So the j will be minus, okay, j will be this times that and that, okay, so it will be minus 1.5 times 0.5 TBC over root 1.25. Okay, this time this and minus these two, minus 2 and b, right? J minus 2 and b. Okay, and then next is k, the z component. The z component k plus k will be minus 1.5 times minus TBC over root 1.25, right? Minus NB. Okay. Right? Equals to 0. Okay. Okay, let's erase this. So this is your equation, but actually though it looks like an equation, you realize that this is vector, so actually you have three components. You have I, you have j, and you have k. So actually in this expression you have three equations. The first one is I equals to 0, I mean the x equals to 0, and then you have j equal to 0, the y equals 0, and then you have k equals to 0. So in this equation you have three equations in this expression, right? So okay, what you want to do? You realize that actually in this k, if you take this z k, you have two unknowns, NB and TBC. So you cannot solve it straight away. If you go to J, this, and this, you have how many unknowns? You have TBC and NB. Same, you don't have, you cannot solve it straight away. But if you go to X component, which is I, right? You see that actually you just have TBC. So if you go to I component, or X component actually, so you can solve, because you can solve it right away, because you just have one unknown, which is TBC. So it is 0.5 times 0.5 times minus 196.2. It is minus 98.1, right? Half of the way. And then plus, plus 0.5 plus 2, it is 2.5 TBC over root 1.25, right? This one, these two they can be sum up. 2.5 TBC root 1 2 equals to 0. So your TBC will be, so TBC is 98.1 times root 12.5 divided by 2.5. It is 138.7. 2.1. Times root 5. Then we find TBC, okay, 98.1. Okay, then we find TBC 98.1 times root 1.25, okay, divided by 2.5, which is 43.7. So TBC is 43.87, right? This TBC. 43.87. Okay, and then we can go to either J or K component, I mean, it doesn't matter, to find the NB, because now you have TBC, right? So probably the simplest one is to go to J component, because it just has one term, right? So the K component, the K component. So we go to this, it is minus 1.5 times TBC, minus TBC, which is minus 43.87, right? Over root 1.25 minus NB, right? Minus NB, and then there is no other K component, J equals to 0. So you can find NB here. NB is, you hit the calculator from the previous 43.7 times 1.5 divided by root 1.2, 1.25. Okay, so we got 58.86. Okay. So NB is 58.86. Right? Okay. So we have solved the two unknowns at point B. Now we have the three other unknowns, the ball and socket reactions at point A. Okay, you have solved this, so basically we need to find AX, AY and AZ. Here, actually again, something you can see straight away is that you can find AX. Because the forces in X direction, there are only two forces in X direction, which are NB and AX. So you do the forces in summation of forces in x equal to 0, right? So you have positive AX because initially you assume AX to be in the direction of positive x, plus NB, which is 58.86 equals to 0. So your AX is actually minus 58.86 Newton, right? So this AX is actually minus 58.86. What does it mean by that? The magnitude is 58.86 Newton, but it actually goes that way, right? Next you can try to find AY or AC. I mean, it doesn't matter. Probably you want to find AY first. So you do summation of forces in Y equals to 0, right? So you have AY with initial assumption of going in positive, along the positive x direction, AY, and you don't have x, okay, you have this TBC. So you have minus TBC going this way. So to have the y component, you have to take 1 and 1 over root 1.25, the same like the way that we did in the vector form just now. Okay, 1 over root 1.25 equals to 0. Of course, this TBC, you can substitute value, right? It is 43.87. So you can find your AY equals to 43.87 divided by root 1.25, which is 39.2. 39.2 Newton. Try to have more decimals, okay? Y and then FZ. Why do we need FZ? Because now you have find AY here to be 39.2 Newton, okay? So you need to find AZ. To find AZ, basically, if you do summation of forces for this road along Z, in Z direction, so you have AZ, you have this weight, and then you have this TBC component, Z1 of TBC, okay? So if you do summation of FZ equals to 0, then you have AZ, positive AZ, right? And then you have minus 20 times 9.81, the weight just now, 196.2, I think. And then the TBC component, the Z component of TBC, which is plus TBC, right? 0.5 over root 1.25 equals to 0. Of course, we have found the TBC. So the TBC is 43.87. Okay. So your AZ, hit the calculator. 43.87 times 25 divided by root 1.25. Okay. And then plus minus. So it is 176.6. Okay. So your AZ is 176.6. Okay. What does it mean by that? Here, in this configuration, the ball and socket here has AX going that way, 59 Newton, going this way, 39 Newton, going up 177 Newton. So you have to find the resulting reaction, okay, by do the Fx squared plus Fy squared plus Fz squared, root of that. But because here actually the question asks to find the components of reactions at ball and socket A, so you can just leave it as AX, AY, and AC. Right, so now you have all the unknowns. And just as again side note, the TBC here you got 43 or let's say 49 Newton, which means that when you choose a cable, that cable should withstand the tensile force of 44 Newton. Right? Same goes to this ball and socket. You should choose a ball and socket that can withstand the load of the resulting load of AX squared plus AY squared plus AZ squared root of that. Okay.